After several weeks of sourcing, it's time to start building the prototype assembly, which will involve sub-assembly and some preparations. Hi, welcome to Slow Engineering, I'm David. I started working with a 4mm thick polycarbonate panels fixed only at the four corners. The panel requires holes for the shafts to pass through and must be strong to maintain its shape. After measuring and marking the centers, I applied paper tape to the bottom sides to prevent cracks when drilling. The holes are positioned 29.2mm from the near side and 22mm up from the bottom of the panel. I drilled the holes to a 6mm diameter to allow 5mm shafts to pass through and provide some tolerance for assembly adjustment. I recommend starting with a 3mm drill, then moving to a 4mm, 5mm, and finally a 6mm drills to avoid any issues. Otherwise, you might encounter a situation like mine. I jumped from the 3mm to 5mm drill. As you can see, the panel stuck on the drill. Additionally, if the drill press does not have a lower speed, it's best to use short bus to avoid melting the panel. The next step is preparing the profiles. I use 2020 profiles, the same as the Voron 2, to blind join the frame. Two profiles will be required for taping the threads and two for drilling the holes. The drill holes are meant for securing the screws once the two profiles are aligned. Regarding the floating bar bone, I have completed the DIN rail cutting. The length of the DIN rail is crucial for the current design. Any excess length will impact the subsequent assembly. The required size for the 350 Voron 2 is 409.6mm. Before cutting, ensure that the two joint parts can accommodate two screws on the center slots of the DIN rail. On the other hand, I prepare the 3D printed parts by making some tolerance adjustments like reaming or drilling before installing the inserts. If you don't want to buy large reamers, you can check my other video which shows how to enlarge holes without reamers. I press all the thread inserts into the 3D printed parts, using the surface to align the inserts instead of forcing them into place works well. You can press the inserts near the surfaces, turn the parts against the table surface, or use a larger tip that can cover the insert and surrounding surface to improve the alignment of the inserts. The first step is to assemble the steppers, which provides precise movements for the floating bar. Ensure that the steppers wires is properly oriented before installation. I use the same 5:1 reduction ratio as the Voron 2 Z-axis to increase the resolution. The 16-2 spoolie is used for the stepper shaft as an input, and it connects to an 82 spoolies with a 188T loop belt. It may be a bit challenging to pull the 82 spoolie shaft into the housing at this stage. Once the shaft is in positions, the remaining steps are straightforward. One corner is fixed at the panel framing part, while the other three corners pass through the panel's framing parts and will be fixed with the profiles later. The next step is to assemble the floating bar. First, slide the dock backplates onto the thin rail and use spacing plates to ensure that the backplates are evenly spaced. Measure the two ends to ensure the joint parts have the same length. Then find the positions where the duct backplates and spacing parts align with the DIN rail slot. Secure them together using screws. It's okay if the slot doesn't match all the insert positions, as each part only needs one screw. As learned shapes interlock them together. I recommend using stainless steel screws for fixing, as the DIN rail groove also serves as an air pass for the tool heads. Hot and fans hot air passes along the DIN rail. Once that's done, secure the ducts to the backplates. The following sequence are used to create a sub-assembly of the joint parts. The sliding carriages I use are 3D printed by EGA's I-180 filament, a material with better self-lubricating features for sliding inside the profile rail. Once the joint sub-assembly is completed, align and secure the joint parts with the floating bar. The holes for optical switches are located on the lower side. Currently, the floating bar weighs around 316 grams. Next, slide the floating bar into the profile frame. This action requires removing the top or bottom profiles and the side of the blind joint screws for the floating bar to slide in. Once the floating bar is placed on the profiles, it's time to secure the optical switches. The optical switches are installed at the joint parts and provide the alignment reference for the Voron 2 floating gantry. While the cables are used to accommodate the movements of the floating bar, and they need to be fixed at the bottom to stay in position. These fixes also act as small clampers and panel supports inside the door, ensuring that the panels is slightly farther away from the profile to avoid friction between the panel and the floating bar. The cable needs to pass through the panel support part, and then two screws on the other part are used to clamp the cable. Before attaching, a screw with an M3 T-nut needs to be installed to fix it on the profile first. The cable will then go through the profile rail and reach outside the door frame. However, there is not enough space for the cable to pass through the frame blind joint, so I considered removing the insulation and letting the wires come out. I didn't like this idea because I wanted to maintain the cable's integrity in case of future modifications. Later, I noticed the center holes on the profile. I printed another drill guide to drill the holes to the centers and push the cable into the holes to reach outside. The upper panel supports also serve as tensioners. The panel support parts are secured with the top profile, and the inner parts contain pulleys and short 5mm shafts to redirect the belts. Long screws with bulging shapes on the inner part guide and tension the belt when they are fastened. After preparing the four corner supports, tape the deep-shaped foam strips around the inner profile edges to ensure airtightness when the panel is in place. Once the foam strips are in place, align the panel onto the frame and insert the output shape through the panel. Then fix the reduction unit on the profiles. Repeat the same procedure for the other side. Install two simple fixings on the top two corners to secure the panel. In the future, a handle or hinges will be installed on the two sides, so the panel needs to maintain its shape without deforming. As mentioned before, the output shaft also needs its shape. After installing the panel, I attached the 22 spoolies to the output shaft. This allows the stepper motor to control the floating bar inside the door. Once the pulleys are in place, the belt pass is secured. The system used two belts to control the two sides independently to align with the floating gantry. The belt starts and ends on the joint parts, then go to the bottom output pulleys, redirect to the top pulleys, and turn back to the joint parts. The joint parts have two belt clampers each, located on both the top and bottom. I installed the belts loosely and adjust the tension using the top pulleys. The floating bar tool changer is nearly complete. I have attached foam strips to seal the gaps between the door and the printer. The remaining assembly work includes installing the door handles and hinges. The following sub-project is the top head system, which involves tool head wiring, a filter system and exhaust, and a cooling system with a CPAP house for the print head. What are your thoughts on the floating bar tool changer? Please share your thoughts below. As always, moving forward.